Welcome back to Bite-Sized Breakthroughs, where we break down complex research into digestible chunks for you. Today, we're diving into a fascinating paper that explores a new frontier in language model scaling. Joining us are Dr. Paige Turner, a leading researcher in this field, and Professor Wud Spectrum, an expert on the broader landscape of artificial intelligence. Welcome, both of you.
Thank you, Alex. It's great to be here. Absolutely. I'm delighted to be part of this discussion.
Paige, let's start with the basics. What's the main focus of this research? What are they trying to achieve?
This paper tackles a critical question. How do we enhance the performance of language models by leveraging vast amounts of data at inference time? We've seen tremendous progress in scaling language models by increasing the size of training data and the number of parameters. But this paper investigates a third dimension, the size of the data store used by retrieval-based language models.
Can you explain what a retrieval-based language model is, Paige?
Sure. Unlike traditional language models that rely solely on data learned during training, retrieval-based models can access and retrieve information from a separate data store at inference time. Think of it as a giant external memory that the model can consult to answer questions or generate text. This allows them to access a much broader range of information than what they were initially trained on.
So they're not just memorizing information during training, they can look it up as needed. That's a big difference.
Exactly. And this is where the paper's contribution comes in. They've built a massive data store called Massive DS, containing 1.4 trillion tokens of text from various domains.
That's a lot of data. What kind of domains are we talking about?
It's incredibly diverse. They've included general web data, books, scientific papers, encyclopedic articles, forum Q&A, code, mathematical texts, and even biomedical articles. The idea is to provide a broad range of information that can be relevant to a variety of tasks.
Professor Spectrum, can you shed some light on why this is such a significant innovation?
It's a game changer, Alex. This research moves us beyond the traditional focus on model size. We've been obsessed with building bigger and bigger models, but this paper shows that we can achieve amazing results by scaling the knowledge base itself. The key is not just the size, but the diversity of the data store. It gives these models the ability to adapt to a wider range of tasks and handle more complex information.
It's like having a vast library at your fingertips. Instead of just memorizing a few books, you can access information as you need it.
Exactly. It's a paradigm shift in how we think about language models. We can now build models that are not just fluent, but also knowledgeable and capable of adapting to new situations.
That's a great analogy, Professor Spectrum. Now, Paige, let's dive into the methodology. How did they go about building and testing this massive data store?
They faced a significant challenge. Building and evaluating a data store of that scale is computationally expensive. So they devised an ingenious pipeline that reorders the steps involved in constructing and evaluating the data store, making the process much more efficient.
Can you explain that in more detail, Paige? How did they make it more efficient?
They essentially rearranged the order of operations. They first built an index over the entire data store, which is a computationally expensive process. However, they only did this once. Then they only need to retrieve a large set of documents for each query and apply subsampling and filtering to these documents, not the entire data store. This dramatically reduces the computational cost. It's like building a library catalog first, and then only needing to search through the catalog to find the books you need.
So, they essentially moved the heavy lifting up front, which is a clever way to manage the computational complexity.
That's a good way to put it, Alex. It's a very smart approach that allows them to experiment with different data store configurations without repeating expensive steps.
Professor Spectrum, what are your thoughts on this methodology? Is this a standard approach in the field, or is this something novel?
It's quite ingenious. We've seen other researchers grapple with the computational challenges of large-scale data stores, but this pipeline is quite effective. It's not necessarily a completely novel approach, but it's a very smart adaptation of existing techniques to address the specific challenges of trillion-token datasets.
And what about the results, Paige? What did they find?
The results were quite compelling. First, they found that increasing the data store size consistently improves both language modeling and downstream task performance. It's not just about throwing more data at the problem. The quality and diversity of the data also play a crucial role.
So bigger data stores are better, but not just any data will do.
Precisely. And this is where Massive DS shines. Its diverse domain coverage allows it to handle a wider range of tasks effectively.
Can you give us some specific examples of the tasks they evaluated?
They evaluated various tasks, including general knowledge question answering, domain specific QA, and reasoning tasks. They found that on knowledge intensive tasks like trivia, QA, and natural questions, smaller models augmented with large data stores outperformed larger models that were trained only on the data they were given.
That's fascinating. So a smaller model with access to a huge data store can be more powerful than a larger model without that access.
Exactly. This underscores the importance of knowledge access over pure memorization during training.
Professor Spectrum, what does this tell us about the future of language models? What are the implications of this research?
It's a significant step forward, Alex. This research demonstrates the power of retrieval-based models and the importance of access to vast knowledge bases. It could lead to the development of more versatile and powerful language models that are less reliant on brute force parameter scaling. We're no longer just trying to build larger brains. We're creating systems that can access and utilize information in a more intelligent way.
That's a very insightful perspective, Professor Spectrum. It's not just about the size of the model, but about how it interacts with the world of information.
Absolutely. And this is where the study goes even further. They not only showed that data store scaling improves performance, but also that it enables more compute optimal scaling trends.
Can you explain that a bit more, Paige?
Sure. They compared the computational cost of training a language model with the cost of constructing and indexing a data store of the same size. They found that constructing a data store is significantly cheaper than training a model on the same amount of data. This means that retrieval-based models can achieve better performance for the same computational budget.
So it's more efficient to store knowledge in a data store than to cram it all into the model's parameters.
Exactly. And this is a huge deal. It opens up new possibilities for developing and deploying language models, particularly those that require a vast knowledge base. We can potentially achieve the same performance with smaller, more computationally affordable models by leveraging large data stores.
It's like the difference between building a giant warehouse to store all your knowledge versus carrying it all around with you. It's much more efficient to have a place to go and retrieve the information you need.
Very well put, Alex. But Paige, this is not without its challenges. What are some of the limitations they identified? You're right, Professor Spectrum. There are still some limitations. One challenge is that while they have a massive data store, it might not contain all the necessary information for more complex, reasoning-heavy tasks. For example, they observed less improvement in tasks like MMLU and MedQA, which require more sophisticated reasoning abilities, and they suggest that expanding the data store to include more specialized data sources might be necessary for those tasks.
It seems like the success of these models is dependent on having the right data in the right place.
Absolutely, Alex. The quality and relevance of the data are crucial. They also acknowledge that their current study is limited by computational constraints, and that further research is needed to fully explore the impact of data store size on different model architectures and pre-training corpora.
Professor Spectrum, what are some of the potential avenues for future research in this area?
This is an exciting area of exploration, Alex. Researchers will need to continue developing efficient methods for building, indexing, and retrieving information from massive data stores. Improving the retrieval process itself is a critical challenge. We also need to explore better ways to represent and organize the information in these data stores to enable more effective retrieval and reasoning.
And what about the potential applications of this research? Where do you see this heading?
The possibilities are vast, Alex. We could see the development of more knowledgeable and versatile chatbots, more intelligent educational assistants, and more accurate question answering systems across various domains. This research could also pave the way for more reliable and trustworthy language models, particularly in scenarios where factuality and source attribution are crucial.
Paige, what are your final thoughts on this paper? What are the key takeaways for our listeners?
This research is a powerful reminder that the size of the data store is a critical factor in determining the performance and efficiency of retrieval-based language models. By embracing large, diverse data stores, we can unlock new capabilities in language models, enabling them to access and utilize vast amounts of information in a way that was not possible before. This is a pivotal step forward in the field, and I expect to see even more groundbreaking research in this area in the coming years.
Thank you, Paige and Professor Spectrum, for this illuminating discussion. This paper certainly paints a picture of a future where language models are not just impressive, but also deeply knowledgeable and adaptable. Until next time, keep exploring the world of AI and join us again for more bite-sized breakthroughs.